Hello and welcome. This is what I'm calling NMR Review Problem 2. You're given the molecular formula in this problem, C6H12O. Calculating the number of unsaturations, we get one unsaturation only. Having the oxygen there makes us suspect that we might have a carbonyl. Let's look at the IR spectrum. It looks like there might be a carbonyl at around 1620 reciprocal centimeters. Now, if you have a carbonyl, you could skip ahead at this point and check the carbon NMR spectrum. There should be a peak greater than 170 ppm in the carbon-13 NMR spectrum, and if you look down at this, we do not have any such peak in the carbon NMR spectrum. So, no. So we do not have a carbonyl. We have an oxygen that is not part of any functional group that we can see by IR. So the IR really doesn't tell us much of anything in this case. Now let's go to the NMR spectrum. In the proton NMR spectrum, all 12 protons are visible by integration. Here we have a methyl, and all 6 carbons are visible in the carbon NMR spectrum, meaning they're all non-equivalent. Okay, so looking at integration and equivalence is always what you want to do first before you get into analyzing chemical shift, and especially before multiplicity. All right, so obvious signals I already mentioned. We have the obvious methyl 3 hydrogen signal. So yes, it does look like we have a methyl group. Do we have your typical aromatic benzenoid type ring, benzene type ring? There ought to be 6 carbons in the aromatic region, and several protons, you would think. So in fact, this is the aromatic region here. If anything, there's only one. That, of course, doesn't make sense. So, no, we do not have an aromatic ring. Further, we would have known that because this would have been 4 unsaturations, not just 1. All right, so let's go back to our methyl group. You see that the methyl group is a triplet. We know methyl triplets result from a system that starts out at least looking like this, where you have a signal here for 3 equivalent hydrogens split 2 additional times, resulting in a triplet. So next to that methyl group, connected to it, is a CH2 group. We have, in the proton NMR, we have a couple of CH2 groups, 3 of them actually. Now let's say we go off on the track that, well, maybe this CH2 group is next to the methyl group. This CH2 group is at 3.7 or so ppm, 3.6 something ppm. That would require that our oxygen's there. You cannot have a CH2 group at that chemical shift, 3.7, 3.6 ppm, without it being next to an oxygen. Notice how this closes this piece off to some extent. What would be the splitting here? It would be 2 hydrogens split 3 additional times. You would expect to see a quartet. Do we see a quartet anywhere? No. So we were on the wrong track on that. All right, so let's take it back, dial it back to where we have our methyl next to a CH2 group. Here's our methyl triplet at, let's call it 0.8 ppm triplet. And let's say that this CH2 is one of these more highly split signals here. What do we count here? 1, 2, 3, 4, 5, 6 lines. 1, 2, 3, 4, 5 lines. So we have a sextet and a pentet. So let's extend this with another CH2. And what does that give us? This signal here for those two hydrogens would be a 2-hydrogen signal split 5 additional times. So there's our sextet. 6 lines, and that is then established to be connected to that methyl group. Now, and also connected to another CH2 group. Now let's look at this CH2 group. It's clearly not just a triplet being split twice. So it also has a CH2 group next to it, connected to it. What would that give us? 1 signal for those 2 hydrogens, split 4 additional times. Yep, sure enough, that gives us our pentet. Now finally, we have our triplet here because we've run out of CH2 groups. That's the one connected to oxygen. And look at this nice piece that we have. We were able to just walk our way through the molecule by analyzing the splitting, which establishes connectivity in every one of these groups. So remember our molecular formula, C6H12O, is that correct? Yes. And we can subtract this group, C4H, 1, 2, 3, 4, 5, 6, 7, 8, 9, H9O, C2H3 is all that's left, along with, don't forget, 1 unsaturation. We have not accounted for our unsaturation yet. So revisiting here, we have these signals left that are more deshielded. Your tables should lead you to suspect this might be an alkene carbon and protons. There's a carbon there at 150 something. So that would give us our 1 unsaturation. And now, in fact, all we have to do is connect that piece on the end here, fill in 3 hydrogens, because that's all we can do, and we have what we call our classic vinyl group. It's a vinyl group. All right, so I'm going to skip on down to the final structure, and the presentation of NMR data for this course would be to draw the structure out nice and big like this and assign all your carbon and proton NMR signals, including the multiplicities of your proton NMR signals, which we can take a look at a little closer here. All right, so we already went through the right half of the molecule. On the left side, how can we explain what we're seeing here in the proton NMR spectrum? We call this actually a doublet of doublets. And let's just for now call each of these a doublet. So remember what I said before, equivalence before splitting. One must recognize that these 2 hydrogens, call them A and B if you want, are not equivalent. They cannot rotate, you cannot rotate around this bond, it's fixed in space. These are always in a different chemical environment. HB is always on the same side as the oxygen. A always opposite or trans. So when they're not equivalent, you get 2 different signals at 2 different chemical shifts. And then here you have, therefore, this proton not being split twice by equivalent hydrogens, but splitting twice by non-equivalent hydrogens. So remember our triplet over here. That is a 2-hydrogen signal split equally by neighboring hydrogens that are equivalent. An equivalent, a split there, and then a split of equivalent magnitude there, referring to this magnitude. All right, that causes essentially the middles to pile up and make it look like what we call a triplet. But in fact, it's a special case of a doublet of doublets. This proton here, okay, is split at 1 magnitude by one of the non-equivalent protons and at a different magnitude by the others, giving you a doublet of doublets. Voila!